Austria. So we do a lot of design and characterization of ceramic components from single crystal to ceramic systems, and now we are entering the field of 3D printing using stereolithography. So the idea today, we'd like to share with you some of the concepts that we have used in the past on how to reinforce ceramic materials, make them more tolerant to damage, and how we can apply these concepts and use them for 3D printing parts. I need to introduce this slide just to draw the attention that many components that we find in ceramic applications are using the casting technology, using a combination of layers of different materials. And so we have been exploring how to use this concept of combining layers in order to reinforce or increase the mechanical strength and damage tolerance. I think we can also skip this slide. We deal with defects in a way that we use inelastic fracture mechanics to describe failure of ceramic and brittle components. We have a probability of failure, and these are the two main parameters we have to deal with. So we have scattering strength, low reliability, etc. And that poses a challenge in terms of design reliable components where the initiation of crack and propagation measuring the functionality. So many of you here in this room know a lot of attempts to use bio-inspired concepts to either tailor the architecture of the ceramic components or acting the microstructure to make it more flow tolerant. So today I would like to go through several questions so we can learn from nature, and we apply it to engineering designs, and at the end see how can we apply some of the concepts to 3D printing parts. This is the fracture of nature made of 95% of inorganic material, and here we recognize on the one hand the architecture is kind of layer architecture, and the microstructure is very interesting. It's made of reflectance with high aspect ratio bonded between some inorganic polymers. And the idea that we had was to, there's been a lot of works joining ceramic with polymers, ceramic with metallic materials, trying to enhance the fracture toughness. We were trying to see how we could do just by joining layer ceramic with ceramics, if we can also reach good properties. And we came out over the years with three concepts that I would like to share with you. One is alternating layers, so two different ceramic layers together with the strong interfaces. Then we realized that it's interesting if we change the location of the layers, we can manipulate the fracture or the regions where the fracture may occur. And last but not least, act on the individual layers and try to tailor the microstructure and see how effective this could be. The processing technique we'll not go into, but it allows you to very precisely put on top of each other layers of different materials, different thicknesses, etc. In the first concept, we make use of residual stresses in the different layers that can come from different means. Many of you are familiar with different thermal expansion coefficients. We can also induce phase transformation in some of the layers, or like they do in Gorilla Glass using chemical reactions. At the end of the day, what you want to have is materials that are strongly bonded, and due to the different CTEs, you can have residual stresses. And depending on how you put the layers alternating, you can have something like Gorilla-like approach where the compressive stresses are on the top, and you can avoid some contact damage, for instance, or make it more scratch resistance. The second approach we've been investigating is to acknowledge that most of ceramic materials, due to processing or say machining processes, they have defects of the surface. We need to live with that. The question is whether we can embed some layers in order to protect or act against the propagation of surface defects. And that means we'd like to have compressive stresses in the multi-layer structure. On the first example on Gorilla approach, so we used that on a project with the industry where they were doing printed circuit boards, and in order to increase the strength of those boards, we just tailor a little bit the microstructure of this glass ceramic composite, and due to the different cities, we could reach a significantly, so say, increase in the strength of these materials. And when you introduce compressive stresses on the surface, you can also have a minimum strength for the material, which is, in terms of reliability, can be very important. The second aspect I mentioned before was to introduce residual stresses under compression behind the first surface layer. And without going much into detail how we do that, we could learn that by introducing high compressive residual stresses, cracks propagating from the surface could be stopped at the interface or inside the layer and provide some damage tolerance. We removed the video this morning because it wasn't working. If you will do the video, you will see a crack starting at the notch and stopping at the first interface. The second question was what happens if we change the location of the layers? And it's interesting that we realized that actually when we have two different systems, no matter how thick the individual layers are distributed, as long as you keep the volume ratio constant, the residual stresses in the individual layers will be the same. So this is a trivial, let's say, outcome for those working on elasticity. But it was the question important on how these, using the same residual stresses but different thicknesses, may condition the fracture process, at least in the first layers. So, well, we said, okay, well, let's try to do that on one single specimen where we have the same residual stresses in the different regions because we have the same volume ratio, but the thickness of the first layer is different. And we did some weight function analysis and some experiments, and we saw that the apparent fracture resistance of material will change depending on where you locate your protective layer. And therefore you can kind of tailor the fracture in the material or protect certain regions from failure. Working with residual stresses can be challenging in the sense that if you only deal with the compressive residual stresses in the bottom, you get out-of-plane tensile stresses causing edge cracking, and the same applies for tunneling cracks. And in this conference, there's one session on finer fracture mechanics. Colleague Roman Papsi gave a talk on prediction, or we call it something prediction of crack initiation on ceramic using finer fracture mechanics. So using this concept, you can also tailor the layer thicknesses of your material, which will avoid the initiation of this type of cracks. The last but not least is about the microstructure. So we can go and say, well, we can join together layers having different microstructure. How do we tailor the microstructure of these texture layers? We use tape casting, where we align some platelets using the razor blade, and during sintering, according to templated grain growth, we end up having these large grains oriented in one preferential direction. And if we analyze the fracture of these multi-layers combining residual stresses and platelets in some of the layers, we can get this type of kind of Napier-like fracture where the fracture resistance is significantly increased. Now, summarizing, we have different ways of one will be just using compressive stresses, the second one is tailoring the architecture, and then introducing or tailor the microstructure. And you can think now of going from planar structure to more complex devices or components. And for these, it is very useful to have now techniques like 3D printing that can allow you this complexity. And our question was, how can we use the 3D printing in order to produce this type of multi-layers? And we got to PhD running in the oven working on 3D printing. One is working on more architecture design, and the other one is on microstructural design. And I would like to share with you just 2 slides from my very good PhD students. The one was trying to use this technology which is based on a layer by layer, the position of the individual layers. You can have several layers of the same material, thin layers of about 20 microns on top of each other. They change the path and change the material and so on. So this is a relatively not very complex architecture, but it shows, so to say, the possibilities. And again, you can use, I mean, the 3D printing to fabricate a material. At the end of the day, you need to sinter, so this is something that you can avoid. And if you have a strong interface, you can use these compressive stresses that will raise the strength of your 3D printing part significantly. So you can kind of manipulate, so to say, your, in this case, aluminum ceramic just by modifying the surface and give a very high strength. The second approach is to use the concept of aligning platelets using tape casting using 3D printing. So in the 3D printing techniques, without going into detail, we have a rotation path where the slurry is rotating, so you kind of align your platelets the same way. And with the platform, you dig in, you polymerize the first layer, do that again, and you build your architecture layer by layer where your platelets hopefully are well aligned. So we wanted to try whether this will work, and we compare with Equiax alumina, also 3D printing. We could see that after sintering, we could have these very nice elongated grains, some remnant porosity that we have to work on, but the mechanical properties are comparable to these Equiax alumina. And I think we see a lot of possibilities here, not only in terms of structural properties, but also functionalities. So with this, I would like to summarize what we learned in the past in terms of architectural design and microstructure. We can apply now for 3D printing parts. And I think what we're targeting now is going into multi-materials. So for 3D printing is now important if you are able to combine soft material with hard material. For teeth, it's important to kind of tailor the compliance of the teeth. Or resorbable materials, biomaterials. These are some examples that we are working on with the company Litos, and yeah, we think that the complexity is very high. And you look at some examples and you realize that we are still far away from those. But I think with the 3D printing, yeah, we can have good applications in the future. So I would like to invite you to the open. I have a lot of colleagues here supporting. Yeah, thanks for your attention.
Thank you, Raul, for presenting us these very clever concepts, very novel ones. So the talk is open to discussion. Any questions? Okay. So I've seen that you have actually, so you're doing by 3D printing, even within one layer, you do several layers. Does it create any problem with some residual stresses between the same layers or not?
The residual stresses will, if the same material will not have.
Or some structural defects.
At the beginning of 3D printing, the problem was the interface, to guarantee a good interface between the layers doing sintering and so on. And also the printing direction can have influences and so on. So there's been already kind of optimization of that.
Okay, so you solve these things.
But when you sinter now, you don't see any sort of individual layer.
Yes, please.
You print these materials or you make these materials, you say you keep the volume the same, but you can change the layout, because you should also change the residual stresses, right? And so the material performance should change, but you said it remains the same. So how does this work?
So you say that if you keep the residual stresses being the same,
how they change if you change the thickness of the individual layers, right?
Within the system, you change the thickness.
Doesn't the material performance change then?
We do that. That's the reason why we do it, because we want to have close to the surface a relatively thick compressive layer in order to have more reinforcement, so to say, without changing the residual stress magnitude, so to say. So it does change. It does change.
Okay, any other questions, remarks? You know, thank you, Raul, again.
Sure.